So hello, welcome to chapter 9. Another day of physics, another week of physics, another chapter. Um this is kind of where the class gets a little more weird. We've been doing straight up mechanics. These last 4 chapters, 9, 10, 11, 12, are yeah, kind of different. Chapter 9, it gets into some kind of weird effects of various things. What happens if you try to change something's shape? Chapters 10 is all about simple harmonic motion, and 11 and 12 is thermodynamics. But just a little more physics we want to get into. However, before I get into chapter 9, last week we had an exam. So, the exam. Highest score was 100. 2 people in the class got a perfect score on it. I would argue one of them, if anything, should have gotten extra credit because there was they thought of something I didn't think of and actually did the problem more correctly than I thought of. The Jake problem, they pointed out that there was 2 ohms, so the tension should have been split, which I didn't is true, but I didn't think of. So the average though was a 64.9. Little lower than I would have liked. To be fair, that average was help brought down because there was some very low scores. This is not including people who did not take the exam. But there's the breakdown. I mean, it's kind of centered in the. I mean, a lot of you got between 80 and 90, so that's real good. A lot of people good around 70 and 80. But it's the 50 to 60 I slightly worry about. With that put in, this is the grades in the class. The average in the class is right now a 72, which is about where I'd expect it to be. Highest score in the class is a 98.56. I don't normally say this, but the second highest grade in the class is a 98.50. So 2 people are basically identical. But yeah, that's the number grades. Really what normally matters more is the letter grades. Though before I go to the letter grades, I want to point out that the cutoff for an F is here. This 50 to 59 range, having 6 people, is kind of a big deal. Oops, shit. No, annotate. Because when you look at the letter grades, it looks pretty bad. The fact that 35% of you are right now failing the class. Of that 35% who are failing the class, as I had just said, 6, 3, 4, 5, exactly half of them have between a 55 and a 60. So those 6 of you between a 55 and 60, it is definitely possible to get that grade back up. The ones lower, it's still possible, but will take a little more work. I'm really kind of surprised there's so many Fs, especially with the average being in a pretty good spot. A lot of these Fs seem to be low homework and lab scores on top of low exam scores. I've said again, if you can't do the homework, you're not going to be able to do the exams. And there was a large number of people who have failing homework scores and failing lab scores. But that's the breakdown as of now. Any questions about this before I move on to other things? I will throw out there I've had some people complain. I've had some people complain about time at the exam, but I also, I can see when everyone opens the exam and when they finish it. A good majority of you finish with time to spare. Well, not majority, at least half. Um, the exam is timed for a reason. Because it's open notes, if I give you infinite time, you'll eventually find it all online. I really want that's why I would say to practice problems. If you find you're doing the problems slow, it's because you're not accustomed to it. If you practice the problems, you'll go quicker. I'm not, you will have longer on the final for per problem. I'll talk about that. Well, I can talk about the final for a second. The final is 2 hours long normally, where the exam is normally 50 minutes long. Um, and there is twice as many problems, but you actually have some extra on time on top. So the final, you will have a little bit more time per problem. They haven't released the final exam schedule, so I don't know when exactly it's going to be. But I would say instead of 4 questions, it's 8. And it's normally, I've been doing 50 minutes plus 15 to upload. This is going to be 2 hours plus 15 to upload. So you're going to get an extra bonus, like 20 minutes total. Well, 10 minutes per full problems extra. So that maybe will help too. So yeah, anything? Okay. One other announcement I want to make then. Don't forget there is no homework due this week because I didn't cover anything. I do need to move my office, shorten an office hour. That says today. That's a mistake. I don't have office hours at all those times today. Um, I do have office hours from 3 to 4 today. But on Wednesday, they're normally 3 to 5. I'm going to shorten them to 3 to 4 on Wednesday because I want to go to an open session to meet a new dean candidate. But since there's no homework due this week, I think it should be okay. But if you would like to meet with me and you were planning on going to that 4 to 5 session on Wednesday, shoot me an email. I'll work something out with you. Okay, am I good to start up then? Okay, I assume nothing else since no one spoke up. So, what we're going to talk about, as I said, is deformation of solids. What happens when we start trying to bend things, or break things, or just twist them, or pull on them? Now, before I can get into the deformation of solids, I need to make sure we're all on the same page with like the next 3 slides. I'm going to kind of go through the next 3 slides a little quick because I assume no one needs to learn the facts that I'm about to be telling you. But just to make sure we're on the same page. The first is that there is 4 phases of matter. We are only going to talk about 3 of them, that being solid, liquids, and gases. And traditionally, how you're taught it is solids have a fixed shape, fixed volume. Liquids have a fixed volume but can change shape, and gases both can change shape and volume. The thing is, that's not exactly true. You see, this balloon is a gas. I can go and I can mold it however I want, and if I compress, I can change its volume or its volume. That is true. And liquids, yeah, they pull. I don't feel like pulling out my water, but if I move the water around, it'll change volume to match the thing. Oh, sorry, it'll change the shape to match the thing, but the volume is fixed. But solids having held a shape. This is a solid, it has a set shape. But I can bend this ruler. That's changing its shape. Solids, it's what it is with solids is you can change the shape, but they don't do it freely. And even that's not necessarily true because this is a solid, and if I let go, it just falls down. It's changing shape pretty freely. Its thing is they won't go fully to mold to any consistency. And actually, what this chapter is going to be about for the first hunk of it is the process of changing the shape of a solid. Of note, the volume of solids and liquids also change with temperature, but we are going to cover that in chapter 11. We're also going to talk about density a lot this chapter, which I haven't really touched on much in this class. So I just want to make sure we're on the same page. Density is defined as mass over volume. In this class, I'm going to use the Greek symbol rho. It looks like a P. It's a rho to represent density. Be careful because we're going to have other things that are P in this chapter. In fact, I'm going to introduce something with P in 2 slides. And this is a rho. I normally like to draw the difference because you have to draw both a lot as the rho kind and the P, that the P kind of has a little solid piece that sticks up there where the rho is smooth. But density, mass over volume. Also, there's going to be a few times where you might need to know, because of density, the volume of an object. Here's just some common equations for volume for some different shapes. Rectangular solid is length times width times height. Cylinder is pi r squared times h. And a sphere is 4/3 pi r cubed. That's just in case you need them. Any questions though? Okay, let's actually get into it. What we're going to talk about for most of today is the deformation of a solid, aka taking a solid and changing its shape. And if I take this wooden plank and start bending it, which actually I'm going to put it here because that's still on the camera. If I take this here and push down and see how much it bends downwards, that's what we're mostly going to talk about. But deformation of solid can also involve breaking a surface. And if I take this balloon and I lost the nail, somewhere there's a nail, and take a nail and push nail into balloon, I pop balloon. That's a deformation of solid. The nail punctured it. And when we talk about deformation of solid, what we normally need to talk about is it's not necessarily how hard you push on something. You see, when I pop that balloon, and let's do it with this guy again. Let's say I take this ball, it's just styrofoam. If I take this, I can push on it. If I decide to push on this ball with 10 newtons of force, not much is going to happen. Likewise, if I go up and pat you on the back, that seems like a weird thing now that I haven't seen a person in real life in ages, and I just push you with 10 newtons of force, it's just going to be like, why the fuck did you push me? That's it. But if I use the same amount of force, and instead of my flat hand, use the edge of a knife, that's going to be a little different, because that's going to probably cut. And even worse, if I, instead of using the edge of a knife, decide to use the tip of this nail, like if I'm going to go up and push it on you with one of these two hands, you're going to hope it's this one, because this one with this nail sticking out, it's going to be a lot more uncomfortable. And even if all of them are at exactly 10 newtons, they will not have the same effect. But there'd be a big difference between a hand, a knife edge, and a needle. You know, yeah, if you go and get the vaccine, they don't push that hard with the needle. It goes right through your skin. If you push just as hard with your flat hand, it won't. And the reason why is because anytime you're going to deal with breaking the surface of a material or deforming the material, aka changing the shape, force isn't all that matters. What really matters is the pressure. Pressure, which uses the symbol P, is defined as force over area. It's not just how hard you push, but the area. If I go up and slap you with this hand, the area in question is the area of my hand. But if I go up and poke you with, trying to make it so it shows up in the camera well, if I go up and poke you with this nail, the area is just the tiny, tiny, tiny point of the nail. It's a much, much smaller area. And therefore, it's a much higher pressure. That's why that can break the surface. And so, yeah, we're going to use pressure a lot in this chapter. Force over area. Now, the unit for pressure, it will be pascals. Well, 1 Pascal is 1 Newton per meter squared. The non-SI units is sometimes you see people use ATMs or atmospherics. ATMs is a unit of pressure where it defines pressure at sea level due to the air as 1, where 1 ATM is 101,325 pascals, or PSIs, which stands for pounds per square inch, where 1 PSI is 6,894 pascals. Just stab the sword into this ball. Okay. Now this explains a lot of things. So let's say if I was to put this nail on the ground and try to lay on it, it would really suck. It would go right into me. But you've seen probably before people can lay on a bed of nails. The reason you can lay on a bed of nails is because you're upping the area. You see, when I took this one nail and pushed it into the balloon instantly popped. But if I instead have a bed of nails, what's going to happen is if I push a balloon into one nail, the entire area that force is applied is just the tip. But if I have a bed of nails, the area that's touching is going to be the sum of all the tips. And so if I take a balloon and put it on, the bed of nails, okay, these are 2 kilogram weights. I forgot how much setup I did for this video. And push down on it, I can apply a good amount of force and not pop the balloon. The reason why the balloon doesn't pop is because the area is spread out over all the heads of nails. It's not just one nail. That much force on one nail, it would have popped instantly with even less force than I did there. It's because you're increasing the area. It's why you can lay on a bed of nails. And in fact, if you want to go really crazy, my high school physics teacher did this next bit live for us. I've never been brave enough. But not only can you lay on a bed of nails?
Mass is spread out, so that pressure is not as great.
But if there was no cinder block to absorb it, and then you absorbed it, would you
get hit by the switch? I'm pretty sure that hurt
Even if you weren't on a bed.
Oh.
Okay, I'm toning him down. So even if you lay on a bed of nails, you can lay on a bed
So
of
the other
nails
thing I do is
because of the
every week
fact
there's
that
a
your area is greater, that your force is spread out
and I
because you
kind of
have
see if
more
you
areas
heard
to
the
all of the nail
Sir Isaac
tips.
Newton.
Even if you were to add more weight,
Now the physics book is just there, so I don't
it's
touch
still
anything
good.
in the face.
Are you ready?
I'm ready.
This is
I'm so excited right now. Ready?
Can't do it.
Oh, he broke the board.
And even applying a lot of force like that, it still won't puncture due to the large amount of area. Now, there is also a few other things at play in that example. Once again, it is not too much pressure because there's a lot of nails of heads, a lot of heads of nails. Oh, actually, the shout part of the nails, not the head, but whatever. And so it's the force is distributed over them. The pressure isn't that high because it's a larger area. The other main reason that's actually safe is because the cinder block broke. Most of the force of swinging down the hammer went towards breaking the cinder block. It doesn't go towards pushing the guy down. So it's actually the main reason that works. If that cinder block didn't break, that guy would probably be pretty skewered. Okay. Any questions so far? Put my nail away before I lose it. Okay. Now, any solid object is deformable. Any object that is solid, no matter how solid it seems, you can eventually bend it, break it, twist it, do whatever you want. The reason why is if you apply enough force, you will bend a thing. And really, it doesn't matter the force you apply, it's the pressure you apply. I mean, force and pressure are directly related. Pressure is force over area. But if you apply enough pressure, you can change the shape of anything. Now, when you start messing with applying pressures and forces and trying to bend and twist things, we can talk about a few different categories. This right here is a shelf from a mini fridge. Let me put something in front of me so I can rest on the ground higher. If I take this and just push lightly, it'll bend a little bit and then bend right back, right? And I can do that better like this. No, let's use this ruler. This ruler is more flexible. That when I bend this ruler, it comes right back to where it was. Oof, I bent it too far. That's sad. Okay, this is gonna get into something I wasn't gonna talk about yet, but I'll get to in a second. We'll save this for later on. Let's use this guy. So if I bend this and it comes right back to the shape it was, that is called elastic behavior. Elastic behavior is anytime when you stretch or bend something, it returns to where it was. I will say that if you apply enough pressure on things, like if I take this shelf and push on it, I can bend it so it stays there. It doesn't instantly, when I remove the force, it doesn't go straight back. If you apply a force and it bends, and when you apply the force, it doesn't go back, that is not elastic behavior. And of note, the equations we're about to cover will only be for elastic behavior. Only be when you push just enough that it whoops, it comes right back to where it was. When you get to the point that it stays in the shape, or even worse, breaks entirely, as in the case of my ruler here. I need a new ruler now. Sorry, I can't believe I just did that. These equations we're going to get into will not count though, because this is no longer elastic behavior. And as long as we're in elastic behavior, so once again, if we remove the pressure, it goes back to its old shape. We can talk about the stress and the strain. Stress is force over area. Now that may seem like what I just introduced pressure as force over area one slide ago. I'm going to talk about that more next slide. But we'll say that the amount of stress you give something is the force you apply over the area it's applied. The strain is how much it wants to change size. Strain is defined as the change in length over the initial length. It's just going to be how long it was versus how far it moved. And these equations are going to be kind of interesting in form, but change it up a little bit. But that's a general idea. Stress is the force you apply over an area, or the pressure. It's really the pressure you apply. Stress is the pressure you apply. and strain is the change in length over length. And what we can say is as long as you are in that elastic region, stress is proportional to strain. What it is that strain times a constant will equal stress. Well, that constant is called the elastic modulus. Now, before I go into more detail on elastic modulus, this whole stress versus pressure thing, they're mostly the same, but they're not exactly the same. Stress is the pulling of the bonds holding together a liquid or solid. And anytime you apply a pressure to a liquid or solid, you cause a stress of the same value. But officially, you cause a pressure, it causes a stress. In liquids and solids, they will be identical. Gases cannot have stress because there's no bond between molecules. Gases can have pressure. I normally will use the term stress when talking about solids, and I'll use the term pressure when talking about gases and liquids, just because that is the standard. But once again, for solids and liquids, stress and pressure is basically the same thing. For gases, stress doesn't exist. But yeah, I'll kind of, as I said, solids are use stress, liquid and gases are use pressure, just because that is the standard. Okay. Now, as I said before, strain times the elastic modulus is always stress. The elastic modulus is basically a way to talk about how stiff a material is, how readily it can go, whether it's something like this that doesn't really want to change shape, or something like this. So I don't want to break this guy, that I can change the shape pretty easily, that just a little bit I can make it really bend, versus this that I have to put a little more force to make it bend. That's what a elastic modulus is going to boil down to. Okay. Now, the thing is, elastic modulus exists in multiple ways because I can do multiple things to something. I can take this and try to stretch it longer, or I can take it and try to bend it sideways. Those are different setups. And so they have slightly different equations, but they both will follow this strain is modulus times stress. Now, for the different setups, if you're going along the length, that is called Young's modulus. Anytime you apply a force on something and the force is along the length, we'll say the elastic modulus is Young's modulus, which uses the symbol capital Y. Young's modulus will have a unit of pascals. This would be if you take a metal ball or wooden thing in this case and try to stretch it longer. It'll get a little longer, or try to push on both sides and make it shorter. It'll get a little shorter. And in fact, in building, this is going to be a thing that if you have a bunch of steel I-beams and put enough weight on top, they can get crunched down a little bit. Now, the pressure or stress is going to have units of pascals because force over area, which is why Y does. The strain has no units since it's change in length over length. Any questions so far? Okay, let's do two example problems, a simple one and a slightly more complicated one. Let's say I got the picture in this, I got at the top. I apply a 1.3 times 10 to the fourth newtons to a steel ball. This steel ball is a ½ meter long. It has a cross-sectional area of 2 times 10 to negative 4 meters squared. What's the change in length? Given Young's modulus for steel. In this equation, F is the force you apply. A is the cross-sectional area. It is the area of this little bit here. What the area is along the length. Y will be Young's modulus. Delta L is how much the length changed. In this one, I'm stretching it, so it's going to get longer. So delta L is how much longer it gets. And L sub naught is the initial length. It's how long it was before we started pulling. What I can do is if I want to know the change in length, I will solve this for delta L. I can multiply both sides by L naught and divide both sides by Y. And the change in length will just be the initial length times the force over Young's modulus times the area. Some units cancel out. and you can get a value. And what you get is 0.00163 meters, or if you wanted to be fancy, 0.163 millimeters. Doesn't get much longer. Things don't really grow easily, especially steel. Any questions? Okay, let's do another problem slightly more complicated. The femur is the long bone in the thigh. It can basically model as a tube of bone. And on an average person, the cross-section of a femur is 4.8 times 10 to the negative fourth meters squared. Let's say we have a 70 kilogram person. And really, I'm saying, let's say someone is 70 kilograms from the waist up. And they go and they stand on one leg, right? If you stand on one leg and you have 70 kilograms from the waist up, how much shorter does your leg get? Given Young's modulus for bone. You want to find what it is? F over A equals Y delta L over L naught. I didn't put the naught on this one. That was kind of weird of me. Have to fix that. Now in this one, the force I applied, I just said it's 70 kilograms above. But if we have someone, and as I said, let's say they're standing on one leg. Oops. Standing on one leg. All of that force above, that is all being applied down. And that force is coming from the weight. So I can say the force they apply will be mg. Mg is a force. And if I want to find the change in length, I just say different order this time. I can divide both sides by y. But I didn't give the initial length. I said what fraction of the length does it shorten? I don't have L naught or L since I forgot to put my sub naught here. I should really fix that. Oh, God damn it. If I don't give you the original length, you can't find delta L. But once again, I say by what fraction does the length of this femur shorten? When I say fraction of the femur shorten, I mean what percentage? If they put in that terms, just find delta L over L naught. That'll be the percentage it's shorter. If I find delta L over L naught, which I can do just by plugging in some numbers, canceling out some units, I'll get 8.9 times 10 negative fifth. That means the length changes by a factor of 8.9 times 10 to the fifth. That it's going to be delta L equals 8.9 times 10 to the fifth L naught. That's the fraction it goes shorter. Any questions though? Okay, this is assuming all of the force is along the length. We're either pushing this shorter or pulling it longer. But I could also try to bend it instead. That if I put this piece of wood here and push down here, this wood will bend up and down. Kind of like I was doing with my ruler before I broke it. So let's not do that anymore. I'll try to best with this guy. That if I hold this steady and push it down on the end here, I can cause it to bend downwards. That's not going to be Young's modulus. Young's modulus was making it longer. This is something else going on by me bending it down. That is called shear modulus. Anytime your force is parallel to one of the object's faces, you can cause a shear stress and a shear strain. And the general equation is the same idea. Stress is elastic modulus times strain. It's just in this case, instead of Young's modulus, we'll use the shear modulus, which uses the symbol capital S. Now your shear stress is the same. It is force over area. But strain is going to be viewed a little differently. Now, shear stress is often used for buildings. And it's saying when wind comes, how much the buildings bend from side to side. And for that reason, we normally just say the initial length, not as L, though this has an L here. I don't know why. I have to fix that. But as H. We'll say that the height of the object is the equation we use there. because it's going to be how hard it is. And the change will be delta x, because that's how far at x the tip moves side to side. Because once again, it's often used in buildings. But this would tell you how much that if I push on the end of this, how much it sways from side to side. Let's do an example. Let's say that same steel bar as last time, a 1/2 meter long, cross-sectional area of 2 times 10 to the 4th meters squared. And the same force, 1.3 times 10 to the 4th newtons. But this time the force is straight down on the end. How much does the end of the ball dip downwards? So instead of F over A equals Y delta L over L naught, I'll say F over A equals S delta X over H. Now, H, once again, is the initial length, which actually won't be changing here. So in this case, H is L naught. I can multiply both sides by L naught. I can divide both sides by S. And by plugging in my values and canceling out my units, I can get a value. Any questions? Okay, as I said, these equations only work within the elastic limit. They only work assuming that when you remove the force, they go right back to where they were. If when you remove the force, it stays in shape, that is another can of worms. That is going to be a slightly different situation. All objects have what is called the elastic limit. Elastic limit is the maximum stress you can add before it does not go back to the old shape. Here, this might be the best way to show this. So with this little guy, so I'm trying to figure out the best way to do this. So if I push it like that much and let go, it comes right back, right? You can see it's moving when I apply the force, and it goes right back to where it was. That's because I'm still in the elastic range. That when I push, it returns. I don't have too much stress. If I had more stress, I pushed, and it stayed bent. That means I left the elastic limit. Once you leave the elastic limit, these equations break down. Of note, though, the elastic limit is just where when you bend it, it stays bent. There is also the ultimate strength. The ultimate strength is the maximum value it can take before it breaks, or the breaking point. This rule, I surpassed the ultimate strength, aka the breaking point. I applied enough force that it didn't just go and come back. Like here goes and goes back. This is still elastic at this point, but if I apply enough, I hit the breaking point. Now that, oh dear God, that shattered, and there was shards of plastic everywhere. This no longer works with the equations at all, because now it's in pieces. Now some objects, there's a big space between the elastic limit and breaking point. This guy stayed bent, and didn't break. The ruler was going elastic to right when I hit the breaking point. Same idea with this like little piece of balsa wood. Is that the second it hits the elastic limit, I also hit the breaking point. They're right next to each other. Brittle materials, the elastic limit and breaking point are basically right at each other. Ductile materials, like this metal, there's a big space between the elastic limit and breaking point. But these equations only work for elastic behavior, where when you remove the force, it goes back to where it was. Of note, every time you pass the elastic limit, you actually do a little bit of damage inside. Every time I bend this and keep it bent, I'm breaking the metal down a little bit inside, which is slowly breaking this. There will come a lecture sometime where this thing finally breaks. It'll be very sad because I'll need to steal a new shelf from a mini fridge. Okay. So these two moduli we had. One is when you apply the force along the length, and one is when you apply the force perpendicular to the length. But what if you don't only have a length, you do all? The last elastic modulus we're going to talk about is the bulk modulus, which do I have a video for this one? No. The bulk modulus is anytime you have a force applying on all of the sides. And it's most commonly used when you talk about something immersed in a fluid. That if you bring something to the bottom of the ocean and the pressure squeezes on all sides, that's going to be bulk modulus. Basically, the idea of bulk modulus is if I take this ball and don't just push it on like along the length, but take it, wrap my hand around and squeeze in every direction, and I apply a force pushing in every single direction along its length, that's bulk modulus. And what it is the volume stress, which is F over A. The A would now be the entire surface area. And it will be a volumetric strain instead of linear strain. Instead of change in length over length, it'll be change in volume over volume. The bulk modulus just says the force over the area is negative B delta V over V. And it's just saying that how much smaller the volume gets would be the force over the total surface area. Now that negative sign is because we normally talk about the bulk modulus for things being crushed. You seldom get problems with things being spread out. And so therefore a large force is going to make the volume smaller. That's the idea, right? That if I apply a large force, I'm going to crush it down smaller. So F goes up, the volume goes down. That's the reason for the negative sign. There's also something called the compressibility, where compressibility is just 1 divided by B. Still good? All right. Here's some constants in case you ever need them. Young shear bulk moduli. Of note, liquids only have bulk moduli. That's because you can't, grab two sides of a piece of water and stretch it out. It doesn't do that. But it can be crushed in volume. You see some things have Young's modulus and not shear modulus. That's because something like this. This has a Young's modulus but no shear modulus. I can grab it and stretch it longer, but I don't have to do any force to bend it. It bends freely, so it has no shear modulus. But it does have a Young's modulus. In fact, this would be even better. This monkey arm. Young's modulus is how stretchy this arm is. But shear modulus, it's just flapping around free. So no shear modulus. So that's why some of those happen. Okay. Okay. Let's talk about something else with this bulk modulus. Oh, damn it. I still can't get over that I broke my ruler. Let's say we submerge something in a liquid. If we submerge it in a liquid, it gets pushed on all directions. That's the bulk modulus. Let's say I have a weird shaped liquid. And I'm actually here. I'll actually do it. I got liquid in this thing. And when I tip this around, what you can see, which is kind of interesting, is that the top of the liquid is perfectly flat with the shape. That no matter what the shape is, how wide these are, it keeps getting a perfectly flat where all the liquids are. You see what I mean by that? The reason for this is that anytime you have a liquid in any shaped material, all portions of the fluid must be in static equilibrium, and all points at the same depth must be at the same pressure. You see, let's say they weren't. Let's say we had right here a value P1 and right here a value P2, and P1 and P2 weren't the same. If P1 and P2 weren't the same, that means there'd be different forces applied. If different forces applied, that would mean that there would be a pressure differential, and there'd be a set of force, so the water would go and be shooting out the edge. If the water is sitting freely and not being like, if I put my mouth to one end and blow hard on it, I'll add a pressure, I'll shoot water out the other end. But if I'm not doing that, if this is just sitting still, all points are in static equilibrium. And if all points are in static equilibrium, pressure must be constant with depth. And I mean that depth by the shortly on the how far down in gravity they are. It doesn't matter what the shape is. See, if I go put it at, let's go to a crazier angle. If I put it at this angle, I can pick any height and say this height right across here. What that means is the pressure at this spot must equal the pressure at this spot, even though they have different shapes. Otherwise, as I said, the liquid would start shooting out of it. Does that idea make sense? We can use that fact to try to figure out what happens with pressure as a function of depth. Let's say we have a thing of water. And let's say in this fluid, I talk about a cylinder of water within the water. I say that let's just make some imaginary cylinder of water. Here it's this darker shape within the rest of this liquid. The top of it has a cross-section area A, and it extends to a depth h below the surface. Right? I can say three forces act on this area of water. Gravity, because gravity always acts on everything. But there's two pressures. The pressure above the water is going to push it down. And the pressure below the water is going to push it up, where P1 is above and P2 is below. Well, if I look at this hypothetical situation, I can say, I can go through Newton's second law, F equals ma. If this isn't moving, I just have a thing of water, so the water inside isn't going. I can say the force is area. And Newton's second law says forces up minus forces down. So P2a minus mg minus P1a equals 0. Now keep in mind the density of something is mass over volume. And therefore, the volume of this cylinder, well, I said it's a cylinder. It's just going to be h times a, because a cross-sectional area a height h. Rearranging, that means the mass of that hunk of water is rho ha. And I'm going to shove that m into my force equation. Now, looking at this term, every single piece has an a in it. So I can divide by a. I'll add rho hg to both sides. And I'll add P1 to both sides. I get this equation. P bottom, oops. I didn't actually add it, I just changed it. So the 1 and 2. P2 was the pressure at the bottom, and P1 was the pressure at the top. And what this says is the pressure at the bottom minus the pressure at the top is rho GH. And this is what is true in general. In general, the pressure of anything in a depth in a fluid or a gas, this works for gases also, is the pressure above the liquid or gas plus the density of the liquid or gas times G times the depth. This is how you find pressure as a function of depth. If you dive underwater and you dive 20 meters underwater, you want to know what the pressure is? This is how you get it. That anytime you are submerged in any material, gas included, this is why there is air pressure. This is the pressure. Okay. Now, most of the time, P naught is the pressure above the liquid. Looking at my picture here, this is open to the air. And so I would say if I wanted to find the pressure at either points A, B, C, or D, because they will all be the same, it's a function of depth, I would say the pressure at the depth would be the pressure right here plus rho GH. Most of the time, the pressure right there is going to be this number, 101,325 pascals. That is atmospheric pressure. That is the pressure of the air at sea level, at least. Of note, that is not really always a set thing. Pressure does change with elevation. Also, pressure changes with weather pattern, but that is the standard pressure for sea level. Side note, that is 1 atm or 14.7 psi. The reason that we have air pressure is that is your depth in the atmosphere. You can actually solve for that number experimentally, because if you want to find the pressure at sea level, you would just say the pressure above the planet, which is space, so space has no pressure. Rho would be the density of air, G will be G, and H would be how deep you are in the air. So it would just be how far away it is from the limits of space to sea level. That's why places like Denver have like special baking instructions, or like why Delhi has a much lower pressure than 101.325 pascals. It's because you're not as deep in the air, so it's a little less. But in general, your pressure will be the pressure on any fluid or gas will be the pressure above the substance plus rho GH. The density of the substance, G, and how deep you are. The shape of the container has no effect. And this is also assuming down, which is why when I was spinning this guy, it's always going to be sitting flat, because at all points the H here is going to be from here to the bottom of the fluid, or from here to wherever I'm measuring. If I want the pressure at this spot, that is not H. What H is going to be is the blue. Well, I didn't draw it very straight. Let's do it green anyways. That green line would be H, not the red line. It'll be how deep down you are, how far straight down in the y-axis. Okay. Interesting thing with air pressure. If I take a balloon, let me grab another one since I popped my last one. If I take a balloon and inflate it, I put some air in. If I let go of this balloon, it deflates. It deflates because air pressure squeezed it. What's happening is right now the air pressure is crunching on this balloon and it's pushing on it. And the reason it deflates is because the air pressure is just and pushing the air out of it. That's why a balloon will lose air. That's why anything that you raise the pressure will lose it. It's because air pressure is squeezing the air out. Fun fact with this is if you take the balloon and remove air pressure around it, which I can do here by adding a stopper there, the balloon will stay inflated without being closed off. It stays inflated because I removed the air pressure from squeezing it. And without the air pressure squeezing it, the air doesn't get pushed out. Also, as I said before, atmospheric pressure does assume sea level. Humans are kind of attuned to a certain amount. If you start really changing the elevations, people sometimes don't feel very good. The reason why is just the lack of depth in air. But that's the general idea, though. Any questions? I got 2 minutes. I next have example problems, but I have enough time to do one of the. No, it's 1 minute now. I'll save the example problems till Wednesday. So that'll be it for today. Really bad conclusion. I'm like, that's it. That's it. I just said no. I don't have segues. There you go. There's a whole bunch of stuff. Any questions? Let me know. I'll talk to you later.